next part of it is, where do we find all of those conversions? Some of them you've got memorized. Some of them are given to you in sneaky fashions that you have to interpret. Right? Your periodic table is a big, big source for some conversions. Right? There's two primary things that you can pull off of it. If we assume our mass on our periodic table is per an atom, then what we've got for our unit, let's just pick a simple atom. Let's pick hydrogen. If we look at hydrogen, our mass says 1.01. What are the units on that number? We're referring to it as an atom. 1.01 AMUs equals 1 atom of hydrogen. Okay. That conversion is pretty useless in most circumstances. Okay, why? No ideas? When we go into the lab, we use our balances. What unit does our balance tell us? Grams. Well, our unit here is AMUs. Do we have an AMU on our balances? No. So number one, it's an issue because the unit for our mass is nonsensical. Okay? How about for the other part of it, the atoms? You use way more than 1 atom. Why? Because if we went through and did the conversion into grams, how small of a mass is 1 atom? Really, really, really small. So we use a lot more than 1 atom. So that conversion factor, while valid, is really only useful in a theoretical sense within the lecture if we're trying to measure really small masses. Okay? So it's just it's like the Snorlaxian Skittle fart conversion. Okay? There really is no use beyond the lecture. But our periodic table also, when combined, when we take the periodic table atomic mass with our AMU to gram conversion, or Avogadro's number, we can then take our periodic table and take that number into something a little bit more reasonable. We can say that 1 mole of hydrogens equals 1.01 grams of hydrogen. So if we now look at our conversion, grams come straight off our balances. That's useful. We can use that. We can weigh a gram. And mole, what was mole? 6.022 times 10 to the 23rd of some substance. So it's a really large number of substances. Well, when we're looking at something that's incredibly small and incredibly light, a mole actually makes sense to work with. Okay? So our periodic table, while it gives us these two conversion factors, the one that you're primarily going to find useful is the moles to gram. The AMU to atom, you will need to use that. That does pop up every so often, but again, it's a pretty useless conversion because we don't work in AMUs and we don't work on the atom level. Okay? So, where do you find those conversions? Periodic table. The other conversion factors that drop out of this can come back to formulas or to equations. So it's understanding what the numbers in a formula mean, what the numbers in an equation mean. Right? So if we looked at, we've got a formula here, and we got a bunch of formulas and a bunch of equations. So let's take a look at H2O. What does the 2 mean in H2O? Okay, 2 hydrogens where? What?
2 hydrogens per 1 oxygen.
Okay, so there's a relationship, 2 hydrogens to 1 oxygen. Is there another relationship there? There's 2 hydrogens in 1 molecule of H2O. Okay, we have those conversions now. So if I now see a substance of H2O and I want to know how many hydrogens are present, I can use this conversion factor that allows me to convert between those. Okay? What happens if I move to sodium carbonate? That was actually not what I meant to say, but since I said it, we'll stick with it. Sodium carbonate. What conversion factors can I pull out of that? there are 2 sodiums per 1 sodium carbonate, and I heard somebody else say the other one, 2 sodiums per 1 carbonate. Are there other conversion factors you could get out of it? There's 1 carbonate in 1 sodium carbonate. Any other conversion factors? How many carbons are there? There's 1 carbon in 1 sodium carbonate. How many carbons are there with respect to the sodiums in sodium carbonate? One carbon is 2 sodiums. So what you're looking at is what do those numbers mean to the overall formula? Right? And you'll notice with each of these I've provided the substance, but I haven't provided the unit. What unit would I use next to each of these? So we'll go back up to that top one. We said 2 sodium ions. Whoops, sorry, I didn't say that. 1 sodium carbonate. What unit can I insert for each of those? 2 what sodiums? Okay, this is an interesting question. You said molecules. 2 molecules of sodium? Okay, we could run with moles, but let's go to the smaller unit. 2 atoms. We wouldn't call it a molecule because it's just a single element. So we'd look at 2 atoms of sodium is 1 okay. Is it 1 atom of sodium carbonate? It's a molecule. We don't want to say mole because a mole says 6.022 times 10 to the 23rd sodium carbonates. So if I have, let's say, 10,000 sodium carbonates, is that really only 2 sodium atoms?
No.
No. So we got to be careful with the units when we go through and convert this. We do run up to this weird issue with atoms and molecules and different units in reference there. It's okay to reference those in that fashion because all we're doing is counting each of those. Okay. You may also notice that if you write out molecule, that you get very tired of writing out molecule. Okay. And I almost cheated already on it. So we typically come up with an abbreviation. So everybody goes through, why do we have to abbreviate the periodic table? Well, because you get tired writing out molecule. We wrote that out as sodium carbonate every single time. You're going to get tired of that too. So we came up with abbreviations. Any idea what abbreviation we could use for molecule? This is where it gets tricky. If we use MOLE, that's mole. Is a molecule different from a mole? Yeah. So we do run into problems in that respect. You'll notice that if I go through and write these out, to specify molecule, I'll write MLC. Okay? Because MLC is not going to get confused with anything else. Right? No other abbreviation carries that. Did we have to use atoms and molecules? What if I have a very large number of atoms? 6.022 times 10 to the 23rd atoms. I can start using moles. So instead of having 2 atoms of sodium, let's say I have 2 moles of sodium. Okay? Really all I'm saying by that is that I have 2 times 6.022 times 10 to the 23rd atoms of sodium. But I don't want to write that all out. So I converted that 6.022 into the term moles. Officially all of that. All right? So then what would I convert that to on the other side? And I want moles of sodium carbonate. And why the number in front? What number did you suggest? 1. What's happening when we convert to moles? We're saying it's 1, come back here, times 6.022 times 10 to the 23rd, whoops, that's a 3, 23rd molecules. That big unit is our mole. Okay? So just like on our periodic table, we could convert but use atoms or we could use moles. When we look at our formula, we can use atoms or we can use moles, depending on what we're trying to go through and do. Most commonly, what do you think is going to be your preferential unit? Atoms and molecules or moles? How often do we work on the atom and molecule scale? Not very often, which means our most common unit will be our mole unit. So we'll deal with everything in the mole scale. Okay? So what does that start to suggest? Well, if you're given a problem and you're not in mole units, what should you do? Convert to mole units. That mole unit can now allow you to convert atoms to other atoms within a formula, and it can allow you to convert substances to other substances. For instance, if we now look at our equation, so this was up from our formula. If we look from our equation, how do I convert water into CO2? Is there a relationship between the moles of water and the moles of CO2? Through this equation. As a hint, I'm going to give you 1 mole of water. How many moles of CO2 do I need to react with it to make my sodium carbonate? How do you know it's 1? Where did that number come from? The coefficient straight out of the balanced equation. Okay? Remember when we talked about unit conversions and we're trying to deal with Killy and all that fun stuff? And I said put your unit factor, put the number in front of the unit and where it started. Well, what's the number in front of CO2? 1. The number in front of water? 1. So I now have a conversion factor between moles of water and moles of CO2. So if we switch this up and say I want 3 moles of water, I give you 3 moles of water. How many moles of CO2 do I need? 3. What did you do inside your head? You've got beautiful little minds here that can process this calculation very, very fast. If I gave you 3 moles of water and I want, erase and shift, moles of CO2, what did you have to do? You did a conversion. Well, we got rid of the units of moles of water by putting it in the denominator, and in the numerator, what did we put in? The moles of CO2. And we said, well, what numbers can I put in front of that? Well, what number shows up in front of CO2 in the balanced equation? What number shows up in front of water? 3 times 1 divided by 1? 3. We now have our answer. Okay? So you guys can do these calculations. The problem is you don't want to write all this unit stuff out. Okay? You like dealing with the nice round numbers. We very rarely ever deal with nice round numbers. You can't do it in your head. So you need this dimensional analysis, this setup, to organize your thought process so that you can check your work and deal with those unit conversions. Okay? So, let's clear all that away. Let's answer the question. 2 moles of sodium carbonate are mixed with 2 moles of water and 1 mole of carbon dioxide. Then how many moles of sodium hydrogen carbonate are produced? Awful lot of numbers floating in there. Okay, so what do we have to do to approach this problem? Write it out. What should we write out first? 2 moles of sodium carbonate. There's our complete unit. What am I trying to convert that into? moles of our sodium hydrogen carbonate. Can I convert those two? What numbers show up in front of those? We got a 2 in front of our sodium hydrogen carbonate, and we have 1 in front of the other. Do I need 2 moles of water and 1 mole of carbon dioxide in this calculation? No. So why was that information given to me? It's not quite to confuse you. Because our answer after this is that we would get 4 moles of sodium hydrogen carbonate, right? 2 times 2.
Because you need the least amount.
Did you have to start with the 2 moles of sodium carbonate? Could have started with 2 moles of CO2. Whoops, it wasn't CO2, it was water. Sorry, my screen, I can't see it. Can I convert that into moles of sodium hydrogen carbonate?
Yes.
Yep, I go through the exact same calculation. Moles of H2O, moles of my sodium hydrogen carbonate. What numbers show up in front of those? 2 and 1. 2 and 1. The number that shows up in front of water in our balanced equation. Okay. So what we're multiplying by is our conversion factor. Not how much we started with. We're trying to figure out what conversion factor comes in there. So the relationship between sodium hydrogen carbonate and water. That comes out of the balanced equation. That has nothing to do with the words. Straight out of our balanced equation. Now we can relate our conversion factor back to the information we were given. And that's where our 2 comes in. Questions? Seeing some flutterings of thoughts and questions, so I figured I'd hold a second. Okay. What about the last one? Couldn't I just as easily have started with moles of carbon dioxide? So we go through and crunch out this calculation. What do I want? I want sodium hydrogen carbonate. Whoops, there's a C in there. Moles of our CO2, moles of sodium hydrogen carbonate. What conversion factor? What relates those 2 units? Okay. We go back to our balanced equation, 2 to 1. Our answer at the end of that is 2 moles of sodium hydrogen carbonate. Interesting. We didn't get the same number for all of those. What does that mean? Okay. That means our answer, first off, isn't as simple as just 4. Okay. If we added all those numbers up, does that work? No, because what that says is that if I have 1 mole of CO2, the maximum I can make is 2 moles of sodium hydrogen carbonate. That's it. If I start with 2 moles of water, the maximum I can make is 4. Okay, well, if we just compare those 2 numbers, what's the maximum I can possibly make under these circumstances? 2. But 2 is smaller than 4. Why is it not 4? We don't have enough CO2 to make any more sodium hydrogen carbonate after we hit that 2. So it's kind of an odd answer that. Our maximum amount is the smallest value. Right? So at the end of this experiment, or for this question, is we'd end up with 2 moles of sodium hydrogen carbonate. The other way that we could phrase this question is, what is the limiting reagent? Right? And in a multiple choice question, we'd go with A, B, C, D. Immediately, what should you do? Why cross out the product? It's not a reagent. Our reagents are our starting materials, our reactants. Okay? So that's a complete misnomer. We've now cut our odds down significantly. We'd probably have an E that was completely nonsensical in this case. Okay? Maybe peroxide or goats. Goats are always fun. Make fun of goats. So you went from a 20% chance to a 3 in 5 chance. Okay, so that's pretty reasonable. And now if you have nothing else, you at least have those two options, or those three options. You've improved your odds. Okay? So now what happens? We then go through and say, okay, which of those produces the smallest amount of product? Because that one is going to control my reaction. So the limiting reagent in this case would be CO2. And my answer comes out as C. Okay. So two ways we could ask the question. How much product is produced? What's our limiting reagent? Both get at the exact same idea and require the exact same calculations. Questions on that? Okay, I'm guessing because you're all falling asleep that you get this. You're kind of tired of it, so let's switch it up. Percent yield. Okay, and we real quickly talked about this at the end of last lecture. If we ran through and did that experiment or built some bicycles, okay, we all know how to build bicycles, and the example I came up with is that you guys make 2 bikes. Good job. Pretty good at making bikes. I make 16. Who makes bikes better?
We do. Well, actually, you do.
With that information, you might say that I build bikes better
Not that.
because I built 16 and you only built 2. Okay? And just because you said that, you started with 32,000 wheels and 32,000 frames and you made 2 bikes. You had an option to make a lot of bicycles and you could only put together 2. I started with 16 wheels and 16 frames. Who did better?
You did.
It's actually kind of tricky. Do the math on that. How did I make 16 bikes if I only had 16 wheels? Magic. Okay. This is getting at the concept of percent yield. What is the maximum possible that we could make? Okay. And then we compare that back to what we actually made. So you get an actual yield. What was the actual result? What did we get out of the experiment? And we compare that to the theoretical yield. The theoretical yield is the limiting reagent calculation. Right? And you'd say theoretically you could make this many. So with me, with the easier numbers, the 16s and 16s, okay, theoretically I should have been able to make 8 bikes. When I make 16, something sounds a little bit weird. Okay? That's capitalism, actually. No, sorry. So what are our units on our percent yield? So if I made 16 bikes and I started with 16 wheels, 16 divided by 16 is 1. I got 100% yield. That's pretty awesome. Can I do that for my percent yield? No, we need to compare the same thing. So it's, I made 16 bikes and I could have made 8 bikes. So I'm comparing the exact same unit, which means when we go through and look at our units on percent yield, they cancel out. They have to cancel out. If they don't cancel out, the calculation you did was completely meaningless. Okay? So we need to make sure that the units that we've got for our actual and our theoretical are identical. So what do you guys think those units could be? Okay, if we went back to our chemistry, what did we start with on the last one? It was sodium carbonate plus H2O plus CO2 went to 2 sodium hydrogen carbonates. Any ideas what units we might use? What do you think our actual yield is going to be? Units of what? That'd be a tricky question. When we talk about our units, remember at the very beginning of this, and I keep referencing this, you need to use complete units. What makes up a complete unit? It's the measurement and the substance. If we're going to look at this reaction, what do you think the substance is going to be in our yield?
Sodium hydrogen carbonate.
Probably our product. I mean, that's what we're trying to make, right? Our product is probably going to be our unit, or part of our unit. So we would probably have sodium hydrogen carbonate in our numerator. And for our theoretical, what does our substance need to be? Got to be sodium hydrogen carbonate. It's got to be the exact same thing so that my units can cancel. Okay, but that's just the substance. What's the measurement that I want to use on this? Moles is reasonable. So if moles is going to be my actual yield, what's my theoretical yield unit need to be? Moles. So you go into the lab, you run an experiment. At the end of the experiment, you measure it out, and you get measured moles of sodium hydrogen carbonate. Is that an easy thing to measure? What is a mole? 6.022 times 10 to the 23rd sodium hydrogen carbonate. So when you go into the lab today, or if you go into the lab anytime, think about when you go to measure something out. Do you count every single atom, particularly up to 6.022 times 10 to the 23rd? No. Okay. Is this a valid conversion? Absolutely. This does go through and give us our percent yield. But as an actual yield, when we come out of the lab, are we really going to report a mole value? Probably going to report a gram value. Okay. Which means if we have an actual yield that's in grams, what does our theoretical yield need to be in? Grams as well. Ultimately, it doesn't matter as long as you use the same unit, because you'll end up doing the exact same calculations. Okay? But for some reason, everybody seems to think that grams is the only way you can do it. It's not true. You can use any unit you want as long as the unit is the same. Okay? Questions about that? Okay, let's take a look at another question. 2 moles sodium hydrogen carbonate mixed with 2 moles of water and 1 mole of carbon dioxide. Does that question sound familiar? Okay, a few heads yes, so some of you weren't asleep earlier. That's good. And only 0.5 moles of sodium hydrogen carbonate are produced. What is the percent yield of sodium hydrogen carbonate? Go ahead and take a stab at that and see what you can come up with. That's a big hint you already did, if you wrote it down, the calculations for most of this. Must be really tired. Too cold. What's the actual yield? Given to us in the question. It's 0.5 moles of sodium hydrogen carbonate. What's our theoretical yield? How did you determine your theoretical yield? I can't spell theoretical to save my life. Rectical. That shouldn't be as funny as it was. Our theoretical yield comes from doing a limiting reagent calculation. That limiting reagent calculation we just did a couple slides back. And that result was that we generated 2 moles of our sodium hydrogen carbonate. Because what was our limiting reagent? CO2 was our limiting reagent. So we go back up to our calculation. We can now throw that in there. 2 moles of sodium hydrogen carbonate. Before we get too excited about doing this calculation, do our units match? Yeah. So now we can go through, punch into the calculator, 0.5 divided by 2, and we get 25%. So that wasn't too bad. Everything was in moles. Everything could convert through nice and cleanly. Okay? So let's make it worse. Well, actually, I guess before I do that, do you have questions about keeping it at the relatively simple level? Okay, then let's make it worse. So what we said was our first part of this problem is going to be going through and writing out our equation. It looked like most people got the equation right. So we'd have to come up with Mg, magnesium hydroxide, plus HCl, goes through to produce. Minimally, we know it produces magnesium chloride. Right? And yes, I know it's not balanced. Give me a second. right? But does it produce anything else? It has to produce something else because where'd the oxygen go? Okay, so the oxygen had to go somewhere. So now we can start to think of what type of reaction this was. There's two answers that would come out of this, either a double replacement or a neutralization. I personally would focus on the double replacement. The neutralization is a very weak application of acids and bases, so I would kind of ignore that one. So if I'm going to do a double replacement, I swap magnesium for the hydrogen, and I would end up with HOH. Most people wrote out H2O. It's not that that's wrong. I see the double replacement better if I write HOH. It's the exact same thing, no difference. Okay? Before I go through and now balance the equation, I have to make sure my formulas are correct. What's the charge on magnesium? What's the charge on chloride? -1. How did you know those charges? Okay, you can either have them memorized or you memorized a pattern off the periodic table. Okay, but you should know those. Is that formula then going to be correct?
No.
What do we need?
2
We need 2 chlorides to balance out the magnesium. Okay, what's the charge on hydrogen? +1. Charge on hydroxide? -1. Okay. Is that formula correct?
Yes.
Yes. Now that my formulas are correct, I can go through and balance the equation. Is my equation balanced?
No.
What do I need to do?
Make it like 9 times.
All right? Make it like 9 times?
You want to do the whole thing, or you just want to know what it's out? Yes. That's right.
You should be at the point where you can balance this relatively quickly. I'm not going to go through and show that work. Okay? Now that we've got the balanced equation, what do we need to do? We now have to run our limiting reagent calculations. And this is where we'll start writing down a lot more work. So in the problem, I said that you should start with your magnesium hydroxide. So 50.6 grams of our magnesium hydroxide. And I want to convert this into what? Moles of...
Magnesium hydroxide.
Okay. Is that the end goal? If I'm trying to determine an actual or a theoretical yield, it's a theoretical yield of what? Magnesium chloride. So I could break this up into each of the individual steps, but if I don't have to, why bother? Okay, so I want to go to my yield of magnesium chloride. What units do we want for that? This is your choice. Okay. Notice most people saying moles, and that was probably because when we did our little percent yield example, we did moles. Okay, so let's take it to moles. Is there a direct conversion between the grams of magnesium hydroxide and the moles of magnesium chloride? No. To convert substances, I need to be in moles. Well, I'm starting in grams. So I don't have that conversion. Can I convert the grams of magnesium hydroxide into something else? What can I convert it into? Moles of magnesium hydroxide. Remember how we were talking about how useful moles were, and when in doubt, what should you do? Convert to moles. So is there a relationship now between the moles of magnesium hydroxide and the grams of magnesium hydroxide? Yep. What is that? Where is that relationship found? That is our molar mass, which is found on the periodic table, or PT. Let's be cool with abbreviations. How do we determine that? You're going to have to add them all up. So magnesium was a 24, oxygen's a 16, hydrogen is 1. I add those numbers up, and I get the wrong answer. What's wrong with that calculation? There are 2 oxygens, and there are 2 hydrogens. Now I can add that up and get my molar mass. What do we get? Okay, I heard a 58.3.
Dropping decimal points.
As far as sig figs go, what I would do is look back to the problem. How many sig figs are given in the problem? 3, which means at no point should I have less than 3 sig figs for any number I introduce. Okay? If you want to do more, that's fine. So was it 58.2 something? 3.1. Okay, so we can put 3.1. It's not going to hurt. That is what units? That is grams per mole. It's a conversion factor. I can now say that I've got 58.31, come on, pen, 58.31 grams per 1 mole of magnesium hydroxide. That's what that unit gives us. Okay, it's not just grams, it's grams per a mole of that species. Okay? So what unit am I in now? Moles of magnesium hydroxide. So my gram has lost. What am I at my answer yet? No. What did I want for an answer? Moles of magnesium chloride. Is there a conversion between the moles of magnesium chloride and the moles of magnesium hydroxide? Where is that conversion found? From our balanced equation. What is that conversion? That's nice, 1 to 1. We now know by running that calculation that we have the moles of magnesium chloride if magnesium hydroxide is our limiting reagent. How do we know magnesium hydroxide is our limiting reagent? We do this calculation again, but starting with hydrochloric acid. Before I do that, what's the number? What was it, 9.7? 8.7. Oh yeah, we needed the 3 sig figs. 8.6 moles of magnesium chloride. I'll leave that up there, but I'm going to go through and erase all the bottom stuff underneath it. Then go through and we start with our HCl. What did we start with our HCl? 45.0 grams HCl. What am I trying to get to? Our moles of magnesium chloride. Is there a direct conversion between the grams of HCl and the moles of magnesium chloride? No? Oh well, we erased that top one. Can I get the grams converted into anything else? I can convert it into the moles of HCl. Where's that relationship found? Go to my periodic table. Hydrogen is 1. Chlorine is 35.45. And if I do this math right, we have 36 that'll be okay. 45 grams of HCl is 1 mole of HCl. Why did I not use a 3rd decimal point? My sig figs are already at 4. I don't need that 3rd decimal point. Okay. What unit am I at now? Moles of HCl, is that the answer I want? Nope. So moles of HCl needs to disappear, and what unit do I want? Moles of magnesium chloride. Do I have the conversion factor there? 1 and 2. Where did I get the 1 and the 2 from? Those were the coefficients directly in front of those units in my balanced equation. What do I get for an answer? Wait, I just heard 2 different numbers. What number?
He gave you the moles of HCl. It's the moles of magnesium chloride is 0.6 something.
0.5? Okay, what are our units? Sorry, not our units. What's our limiting reagent? Okay. Which one generates our smallest yield? Our hydrogen chloride. or HCl. So that means all of that work that we did for that conversion, oh, so unfortunate. But we needed to do it to prove that HCl was our limiting reagent. Okay. So now that we know our HCl is our limiting reagent, what do we do?
Percent yield.
Now we can go to our percent yield. How do we calculate percent yield?
Actual over theoretical.
Actual over our theoretical. That says theoretical. Times 100%. What was our actual yield?
0.3.
What was our actual yield? 60.0 grams of our magnesium chloride. That's what the chemist actually obtained out of the experiment. All right, that came out of our problem. We now divide this by our theoretical yield. What's our theoretical yield?
Didn't you change to 60 grams in a mole?
0.605 moles of magnesium chloride. We just did that, right? Do those units cancel? No, which means this calculation is meaningless. We have to make sure that the units cancel. So what do we have to do? We can either convert the grams to moles or we convert the moles to grams. Either way, we're doing the exact same calculation. Okay? So for some reason, I like converting to grams, so I'm going to go through and do that. We have our 0.605 moles of magnesium chloride. I want grams of magnesium chloride. Is there a relationship between the moles of magnesium chloride and the grams of magnesium chloride?
Yeah.
Where's that relationship found? From our periodic table. The numbers we put in there would be 1 mole for sure. Anybody actually calculate what magnesium chloride was? 95.2 grams of magnesium chloride, which gives us our theoretical yield in grams. And punch in our calculator, and we'd end up with our percent yield. So only in 15 guided minutes did we solve one problem. Yeah, it's a bit rough. Okay? This entire process is something that every chemist has to do every time they do an experiment. Okay? Theoretically, it gets faster. Yes?
That actually worked out to less than 6 grams.
So anybody actually do the calculation on that? Give me some numbers. What was the grams of magnesium chloride?
Well, I think
57.6.
What was it?
57.6, I think.
57.6. Can I get a confirmation on that? 57.6 grams, which means our percent yield is 104%. What the frick is going on? Science sucks. Sometimes you will get a number that doesn't make sense. Okay? On an exam, we would probably give you a number that made sense so you don't panic too much. Okay? But in the lab, is it possible to get higher than 100%? Yes. Why? Because we screwed up. Was it actually a dry mass? No, it probably actually had some water in it, which inflated the mass number of our actual yield. Well, if the actual yield number gets bigger, what happens to the percent yield? It has the potential to go above 100%. It was supposed to be much more dramatic than that number, but I apparently looked at the numbers wrong. What's that? Could be humid outside, absorbing some of the water in your mass measurements. Okay, so there is some kind of experimental error. That doesn't mean our whole process is wrong. What we would probably do as a chemist is really quickly panic mildly and go through and check our calculations, verify that we were right with our calculations, then bury that experiment and try it again and hopefully get a number less than 100%. Because scientists are really bad at that. We get a bad result, what do? We pretend it didn't happen and we try again. All right? Yes?
Well, I noticed in homework, the percent yield questions are pretty easy because
Yes.
they were giving you
And that's the level that you'll get on the exam too, is the straightforward ones. We'll give you the actual yield and the theoretical yield. They don't typically overlap them. The only reason we overlapped them here was because this takes you through every single step that you've learned across the last 2 exams. Okay? So it's trying to get you to see that it's not independent subjects, that each of these materials do overlap. This problem just happens to overlap a lot. Okay? We typically would not ask this question on an exam because it overlaps so much that if you didn't know how to convert words into formulas, right from the get-go you can't answer the question. Okay? So a lot of the way the final is structured is to test a single subject matter. Okay?
You might have every single one of those questions just separate.
What's that?
So you have every single one of those questions, they'll just be
Broken
separate.
out into steps. Yep. So yeah, there we did. I'm going to delete all that. What do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Probably 10, 11, 12 calculations. So this one problem on an exam would be broken into 12 questions. Right? With potentially no clear overlap that it's happening. But there are 12 questions to be answered as far as the material goes within this one question. Kind of heavy. Questions about that? Okay, so I thought we were going to get further, but I knew these questions were hard, so it's fine. The next section that we'll real briefly talk about is something known as empirical formulas. It is your fully reduced whole number ratio of elements within a compound. Okay, that is what the empirical formula means. It's kind of an odd thing to talk to you guys about because all of the formulas that you've been working with have been the fully reduced ratio of all the elements. You've actually been looking at the empirical formula. Where empirical formulas make a little bit more sense is when we look at more complicated structures. Okay, so let's take a look at a couple quick examples. What's our formula for sodium chloride? Hopefully you get NaCl. I could write Na2Cl2. Do the charges still balance? Yeah, I could write Na3Cl3. Okay, why do we not do that? In an ionic compound, we represent our structure by the smallest whole number ratio because the unit itself, or that repeating unit of NaCl, happens indefinitely throughout the whole structure. If I went out and drew magnesium chloride, we get MgCl2. That could be written as Mg2Cl4. Okay? But again, for the same reason, it's still representing the exact same structure, so I can condense that into a smaller piece, and what we use is the smallest whole number ratio. Okay? So you've seen empirical formulas before. It's just our smallest whole number ratio. But what happens when we move up to a different class of compound? Okay? For instance, something like benzene. Okay? Benzene has this structure, which you'll have to give me a little bit of time to draw it out. There's our structure for benzene. What's its formula? C6, H6. That is the formula for benzene. What is the empirical formula? C1, H1, or just CH? Okay. When we think about the compound of benzene, very rarely will you ever see someone reference it as CH. Why? Because how many carbons are in benzene? 6. Okay? This unit is connected in this fashion. If I look at a larger structure, I'm taking a whole bunch of these units and repeating them out. I need 6 carbons and 6 hydrogens to make that smallest unit. Okay? So the formula becomes almost or odd in comparison to the way we've been looking at it. So the way we've been looking at it is primarily with our ionic compounds, and our ionic compounds repeat at the smallest unit. But molecular compounds don't necessarily do that. So what we end up referencing now is this idea of an empirical formula. Oh, crap. I guess that's supposed to be an I. An empirical formula versus a molecular formula. Okay? And how do we get those individual pieces of information? Okay, well, what did our formula up here mean? How many sodiums are in sodium chloride? 1. If I give you 1 mole of sodium chloride, how many moles of sodium are present? 1. If I give you 50 grams of sodium chloride, how many grams of sodium are there? You should be pausing. Our equation only allows us to relate the number of the species, not the mass. Okay? So it's how many individual atoms go into it. So when we look at an empirical formula, it's ultimately a representation of the moles, or the number of atoms within each of those structures. Okay? So if we were given a different situation, okay, if we had an unknown compound of radium oxide, so this now goes back into the experiment, okay, and we're still dealing with an ionic compound in this case. I've got an unknown compound that has radium and oxygen in it. So we could go through and say I have Ra and I have O. Anybody know the charge on radium? I guess it's +2, but it's really low on the periodic table. That's kind of out there. So we probably don't know its charge, which means we don't really know the x's and the y's. It's the number of those to balance out the charge. Right. If I do this unknown compound, and I find that it contains 0.726 moles of radium and 12.3 grams of oxygen, I could now write this out, or change this equation now, my formula, to being R, where I have 0.726 moles, and O has 12, oh, I had to switch those units on me. Okay, and O has some unknown number of moles within it. Except when you look at a balanced formula, do we see these fractions? No, because we're going to the smallest whole number ratio to count how many atoms individually go in. So our formula doesn't really make sense. Right? And we for sure would not bring this grams into our calculation. So can we determine how many moles of oxygen belong in my formula?
Yes.
How do you do that?
Convert the grams.
Convert the 12.3 grams into moles. How do we do that? Whoops. What's wrong with what I just wrote? Give me the full unit. Grams of oxygen. And I want to get to moles of oxygen. How do I do that? 16 grams of oxygen is 1 mole of oxygen. I now know the moles of oxygen. If I punch that into my calculator, I'm going to get some weird decimal value. 0. Oh, did you just list out the number? Oh, wow. Okay, yeah, I guess you're right. Something like that. So that could be my formula. That's still a pretty ugly formula. What could we do? We want the whole number ratio, so what do we do? Divide by the smallest number. What am I going to get? R1, oxygen, ballpark 1. So my empirical formula becomes RaO. There's our empirical formula. We will pick up there on whatever it is, Tuesday.